you're familiar with the various types of DC motor controllers and how they operate. Right now, we're going to go over some techniques you can use when you're troubleshooting DC controllers. And then we're going to talk about two kinds of maintenance work: preventive maintenance and corrective maintenance. You know, anybody who could handle a .45 might have passed for a troubleshooter in the Old West, providing they could get the mail through or save a lady in distress. But you need to pack more than a pistol to be a troubleshooter in the plant. To troubleshoot an electrical system, you may need to draw on lots of different equipment: diagrams, charts, meters, hand tools. And you have to know how to integrate the information you learn from all these sources. People are another extremely important source of information. Asking an operator what's wrong could save you lots of time. You might be able to learn more than just what isn't working. With a little luck, you might be able to learn if part of the system is operating correctly. You can't solve a problem in a vacuum. You have to understand the system in which the problem occurs. Once you understand how the system's supposed to work, you can eliminate those areas that are operating correctly from consideration and isolate the problem. It's finding the problem that's difficult. This is where you concentrate your energies, devising a strategy and carrying it out. More often than not, making the actual repair is the easiest part of a troubleshooter's job. Now, in this segment and the two that follow, we're going to go over some important techniques you might follow in troubleshooting any electrical problems, because electricity is probably used to operate or control most of the systems in your plant. You could be called to troubleshoot a lighting system in the morning and a lube oil pump after lunch. No one expects you to know how every electrical system in the plant operates your first day on the job, but it's essential that you learn about each system as you go along. Information gathering is a skill, one you've got to develop. Now, Hal just picked up a work order that says a burner tilt motor won't run. Now, that's not much information to start troubleshooting with, but it's all he's got. Now, since he knows he'll be dealing with a motor, he's preparing to troubleshoot a motor as well as a controller.
Hey, Bill, what's wrong?
Burner tilt motor won't run.
Which one?
Right rear.
What's it do?
Nothing.
Won't raise or lower, huh?
It'll raise, but it won't lower.
Won't lower at all?
Nope.
Okay, you operating my hand?
Yep.
Okay, I'll check it out, see what we can do about it.
He's in better shape now. He's got more to work with. He knows what system the problem's in, so he can get the diagrams and charts he's going to need. He also knows the motor will run in one direction, but not the other.
Hey, Bill, this is Hal. Yeah, it's a burner tilt system. How about bringing the schematic and the books and anything else you can find, so we can find out what's wrong with this thing. All right.
The troubleshooting process is underway. He's already learning a lot about the system, and he's got to sort it out. At first, it seems to be nothing more than some isolated information. He knows that it's a reversible motor, that the motor does run, and that the master switch for the system's operated by hand. But those facts tell him a lot. To start with, he can eliminate the motor as a problem because he established that the motor runs. The raised circuit can be eliminated as well because the operator said it works. What else? Well, he can eliminate overload protection. If overload contacts were open, the motor wouldn't operate at all. Now, at this point, he can concentrate on the operation of the lower circuit. As you can see, the strategy to use when you're troubleshooting is divide and conquer. Each time you divide up the circuitry and eliminate a section, you've made progress. You'll be able to zero in on the problem by a process of elimination.
There's no point in opening it yet until we find out where we think the trouble is.
A schematic of a controller will always show two circuits: the motor or power circuit and the control circuit. Since the raise and lower circuits make up the control circuit, that's the area to concentrate on now. According to the schematic, there are two reversing contactors, RRR and RRL. The legend would indicate which one is in the lower circuit. right rear burner, reversing contactor coil, lower. That's it. We need to check the remainder of the circuit to find any other components that could keep the system from lowering. Now let's see what we've got. There's a limit switch. It opens a circuit when the burner reaches the limit of its travel. There's something marked BECS. So, back to the legend. It's burner elevation control switch. Okay, this would be the master control switch we saw at the control station. Well, those are the major components in the lower circuit. One of them, the contactor coil, operates the contacts in the motor circuit. So that's the best place to start looking. Now, I say start because at this stage there's not enough information to conclude that the problem's inside the controller. It could be the limit switch on the tilt mechanism or the control switch at the station. But within the controller, we've narrowed our search down to the contactor coil, the contacts themselves, and the wiring. He's verified that power is off. Now he can check out the controller. Look for obvious things first. Pull on the wires to make sure they're not loose or broken. The contacts look good at first glance. Now you have to push contactors closed to make sure they're free to operate.
What's wrong? Yeah, something's got it blocked and won't close. What you got? Yeah, maybe this is it. It's a nut here. See if you can find the bolt that thing came from. It'll cause us trouble eventually.
That was a mechanical problem. They couldn't have found it with a meter. They had to literally look for it. The strategy they used to troubleshoot this equipment was sophisticated. The visual check was simply common sense. But it's an essential part of the process. As you gain experience, you'll realize that many times mechanical problems cause electrical failures.
Yeah, go ahead and test it. Okay, they're testing it.
Yeah, I wish it was all like simple.
Before you go on to the material in your text, let's sum up what they actually did. Now, they gathered up every piece of information they could get, from the work order to the conversation with the operator. They used charts and diagrams to understand more about the system and better isolate the problem. They continually analyzed each new piece of information, using it to zero in on their target. And because each step was carefully thought out, they were successful.
Electric shop, Hutch speaking. Yes, Warren, I can't hear you. Speak up. Which one? Okay, I'll send Hal over. Hal, how about going over and check the emergency seal oil pump on 16?
See what's wrong with it?
Yeah.
They're going to work on an energized unit this time. Now, this happens to be the most convenient way to troubleshoot this piece of equipment. Whenever you're working with something that's hot, take the proper precautions. Learn your plan's safety procedures. Follow them and stay alert. Now, since they've got so little information to go on in this situation, all they know is that the motor on the pump won't run. They'll be relying heavily on charts and diagrams to locate the problem.
Now let's check the power, make sure the power's on. I'd hate to start digging through this thing and find out somebody turned the power off on us. Okay, your power's on. Okay, let's see if we can find out what caused the thing to quit.
Reading the diagrams for a system will help you determine how it works. Now let's start with the schematic of the motor circuit. we need to find out what kind of motor it is. The diagram shows two fields and an armature, but both fields are starred. The schematic indicates the stars mean if used. Well, at least two options exist. We could check the nameplate if the motor was nearby, but it isn't. So we'll refer to the as installed diagram. This is a diagram that tells us what is actually installed. The as installed diagram identifies which of the starred fields are in the motor. Okay, according to this, we've got a compound motor. A glance at the control circuit shows more starred components and some blocked out areas. Before we go to the as installed diagram, we have to find out what the symbols mean. PS is a pressure switch, and CS is a control switch. Neither of these would be inside the controller. The pressure switch would be somewhere in the seal oil system, and the control switch would be on the control board in the station. Well, what does the as installed diagram say? They're used, but we have to know more than that in order to be able to run through this system in our minds. The control switch has 4 sets of normally open contacts. These contacts open and shut according to what position the master switch is in. Since all switches have at least 2 positions, manufacturers include a switch development chart along with the other diagrams of the system. The switch development chart shows which contacts are open or closed in each position of the switch. This one has 3 positions. In off, all contacts are open, as we saw in the schematic. In automatic, contacts 3 and 4 are closed, and 1 and 2 are open. In run, all 4 contacts are closed. Spring return to automatic. Now, here's another piece of essential information. This means that when the operator takes his hand off the switch, it returns to the automatic position. There's only 1 set of contacts for the pressure switch. The as installed diagram tells us they're normally open. Since this is an emergency seal oil pump, it only goes into operation when the seal oil system pressure drops. So these contacts will close on a pressure drop. The contacts return to open when pressure rises. Well, we've covered all of the components in the control circuit except these 3 operating coils. The book for this system has what's called a nomenclature chart. It serves the same purpose as a legend. All right? MX is an auxiliary relay to M. That means it performs an intelligence function for the M contactor. In fact, the diagram shows that it's actually part of the maintaining circuit for the M coil. MX operates at the same time M does. The M coil operates the line contactor. It connects the motor to the line. 1A is an accelerating contactor. This type of device is used to remove resistance that's placed in series with the armature. When the resistance is removed, the motor speed increases to normal. TDAD stands for time delay after de-energize. That means these contacts close a predetermined period of time after the 1A contactor's de-energized. Well, we've identified all of the major components in the system. Now we need to trace a current path through the controller so we can see how the system is supposed to operate. Now, you've got to understand how a system works before you attempt to troubleshoot it. We've had to do a lot of cross-checking from one diagram to another to get this far in the process, and we'll need to do a lot more before we're through. Information gathering is one of the most important skills you'll acquire. Knowing how to cross-reference these diagrams is an essential part of the information gathering process. Now, back to the schematic. All we know is that the motor won't run. The purpose of the controller is to operate the motor. In order to do that, this set of M contacts must be closed. Therefore, the M coil must be energized. So let's trace a current path through the schematic to energize the M coil and get this motor started. Beginning at line 1, we go through the overload heater, down this line to our control switch. Since contacts 3 and 4 are closed when the switch is an automatic, we have a path to this junction. And by the way, a junction is a point at which 2 or more wires are connected. If we follow this line down, we'd have to stop at these normally open MX contacts, so that's not our route. Back here we see another option. We know these contacts must be closed when the system pressure is below normal. So we can go from junction 4 through the PS contacts to junction 5. From junction 5, the only path we can follow is through these normally closed M contacts, then through the 1A coil to line 2. The 1A coil is energized and operates its contacts. The question is, what effect does that have on the motor circuit? Well, this resistor is now in series with the armature. And down here, we've got a path for current flow through this 1A contact. So the M and MX coils are energized and their contacts operate. And we've got the motor started with resistance in series with the armature. The purpose of that resistance is to protect the motor on starts. So now we want to remove that resistance. This is where the accelerating relay comes in. Here at the control circuit, you can see that with the M contacts open, the 1A coil is de-energized. After the delay, its contacts operate. So we've bypassed the resistance. The motor accelerates to normal speed. The oil pressure rises to a normal level, and the pressure switch contacts open. The motor continues to run, though, because these two sets of contacts, in series with the M and the MX operating coils, are closed. This is the maintaining circuit we referred to earlier. Sometimes it's called a sealing or seal-in circuit, because as you can see, the contacts complete the circuit to the very coils that operate them. Well, that's how the system is supposed to operate, but the motor won't run. We've got a pretty good idea of the sequence of events that should take place now, though, so we're almost ready to look inside the controller, but not quite. You see, at first glance, all but the simplest types of controllers look like a jumble of wires, junctions, and hardware. You need a wiring diagram to find your way around. The wiring diagram indicates the physical location of the components and the junctions in the controller. But even then, it's not a lead pipe cinch to find them. Wiring diagrams are best used along with schematics. You can use the schematic to identify more than just the number markings on the component. You can also use it to learn what major components the electrical junctions are connected to, and that will save you a lot of time.
Let's check see if any of these things are operating. It looks like 1A has. Hey, that's a piece of luck. Give us a place to start anyway.
If 1A is operated, that means the control switch is okay, and the pressure switch contacts are still closed. Both the MX and the M coil should be energized because we've got a direct path through this 1A contact. Here's where we start. If this contact is closed, we should get a reading between 8 and 6. To find junctions 6 and 8 on the wiring diagram, we need to refer to this schematic a little longer. It shows that junction 6 is connected to a 1A contact. Well, that means we're going to find junction 6 somewhere on the 1A contactor. Down here, we've got what's known as a common connection. These three coils are all connected at junction 8. That means we're going to find junction 8 right near the 1A coil. The first thing we'll look for is the 1A contactor. Here's the coil, and to the right of it, junction 8. The 1A contacts are here, and right in the middle of the 1A contacts, junction 6.
Okay, 1A relay's closed, power's on. Let's take a reading between 6 and 8 and see what we got. We should get a reading if this contact's closed. What have you got? Nothing. I'm going to open our someplace. Let's see if we can narrow it down a little bit.
The more they eliminate, the easier it will be to solve the problem. The schematic is what they need at this point. Checking between points 5 and 8 should do it. We know we have a complete circuit from junction 5 to L1 through the closed PS contacts and the control switch. Junction 8 and line 2 are actually the same circuit, so there's no question here either.
Okay, junction 5 should be up here near 6. Yeah, there it is. You got it? Yeah, that's good.
That 1A contact's not closed. Now they'll see to it that the system's de-energized and examine the 1A contacts to see what's causing the problem.
Well, we gotta get the power turned off, this thing tagged out. You wanna call Hutch? Yep.
Well, the troubleshooting was successful. This time, all they had to go on initially was the name of the system and the fact that the pump wouldn't run. Working on an energized system demands extra caution, but the approach you use is the same, observing all safety procedures and keeping the potential danger well in mind will keep you safe. They spent a lot more time poring over those diagrams than they'll need to actually make the repair, but that's not unreasonable. Most of the information they needed was locked into those charts and diagrams. Knowing how to use them was the key to solving the problem. There's a diagram of this system in your text along with a sample problem for you to solve. But before you begin, let's go back and watch them test operate the controller.
Okay, the power's on. Now looks like all 3 coils energized. 1A dropped out. That's it. Let's go.
If normal safeguards to a critical system fail to operate, hundreds of thousands of dollars worth of equipment could be damaged. Most plants have backup systems to help eliminate that possibility. Now we're going to look at an emergency lubricating oil pump system next. The pump's designed to start automatically and provide oil to the equipment if the normal pump fails. The system has a feature we've not seen before. It's an indicating light that tells the operator it's ready to run at all times. A sense of urgency develops when a feature like this indicates a problem. It's the kind of warning you're primed to act on as quickly and efficiently as possible, because it could mean the backup system would not operate if it was needed.
Electric shop, Hutch speaking. What is it on? Yeah, okay. Is the green light the only problem? Okay, somebody's on the way.
The operator just told Hutch the ready-to-run light for the emergency lube pump is out. Hal's first move would probably be to pick up a light bulb on his way to the control room. He'd ask the operator what happened. After he'd learned as much as he could, he'd check for obvious things. He'd replace the bulb, then he might check the position of the switch in case somebody bumped into it. Common sense and a sharp eye can save you a lot of time and effort. Well, no quick solution this time, so diagrams are the next logical source of information. This time there's a lot of information to start with. We know the green light's a problem. We can zero right in on the circuit containing the light and work from there. Eliminating all the other circuitry from consideration is a valid approach to troubleshooting in this kind of situation. In order for the green light to work, there must be current flow from L1 through the light to L2. If we test each component in the circuit for continuity, the control switch, the time to open 2A contacts, the MX contact, the resistor in series with the light, and the M coil, and then check the wiring, we should be able to further isolate the problem. We'll use a multimeter to test for continuity. The meter's set up to indicate the resistance of each component. If we get a reading, we know there's a complete path for current flow through the component. If there's no reading, that means there's an open within the component. A contact isn't closed, for instance. And by the way, never use a multimeter that's set up to read resistance on an energized circuit. That's a good way to destroy the meter. Always shut off the power to the system and get it tagged out before you start to test. Now, before you put your hands in the controller, double check to be sure power's off. Then look the controller over carefully. If there's a broken wire or a loose connection, now is the time to find it. Operate the contactors by hand to be sure they're free to move. There's no substitute for a thorough inspection at this stage of the troubleshooting procedure. The next step is to locate the components in the controller. Use both the schematic and the wiring diagram to do so. Only 3 of the components we want to test are in there. According to the wiring diagram, the 2A contacts are here on the 2A contactor. The MX contacts would be on the relay. The M contactor is where we'd find the M coil. They'll test the M coil first because unless the M coil's good, current can flow through the circuit. Standard practice when you're testing for continuity is to disconnect one of the wires leading to the component before you apply your leads. And that way you can be sure you're not reading through any parallel paths. With a lead on each junction, he's got a reading. So this component can be eliminated. The next component tested should be the MX contacts. They'll use the schematic to figure out which junction points on the contactor to test. Okay, he disconnects one wire from the contacts, closes it by hand, and then puts the leads on junctions 3 and 4. He gets a reading here too. Well, the only component left is the 2A contacts. He prepares to test the component just as he did before. He disconnects one wire, closes the contacts by hand, and puts a lead on each junction. No reading this time. They've zeroed in on the problem. Now they'll pull 2A and look over its contacts. One of them's not making. The hardest part, finding the problem, is done. All they need to do now is decide whether they have to replace the faulty contact or repair it. This time, Hal and Rod were able to go directly to the problem area in the control circuit, ignoring the remainder of the circuitry. This is a prime example of how the elimination technique can really save time. But don't confuse saving time with taking shortcuts, though. Troubleshooting is detailed, painstaking work. Logic and order are what all troubleshooting procedures are based on. Now, there isn't much luck involved. Hunches and shortcuts just don't pay off. An organized, systematic approach does. Each time you go out on a job, remember these 4 steps. 1, gather all the information you can from the operator and anyone else familiar with the equipment. 2, learn how the system's supposed to operate. Charts and diagrams are usually the key to understanding the system. 3, make a thorough physical inspection of the unit. And then, based on the information you've acquired from steps 1 to 3, you can go ahead to step 4. Determine which tests you need to make to isolate the problem completely. As we said, solving the problem's usually pretty easy to do. Finding it is hard. Well, it's about time to go over the material we've just covered in your text. You'll find some diagrams there of the system we just worked on, a switch development chart, and another problem to solve. See if you can get this motor operating at normal speed. Now, bear 2 things in mind. 1, the system only operates after a pressure drop, so the pressure switch is closed. And 2, in order to get the motor to run, you're going to have to set the controller in automatic. Okay, before you start, though, let's go back and watch them do the final check on that component. He's testing for continuity through that contact to be sure the repair's good. Okay, the light's on. This job's done.
Hey, John, I just got a call from Bradshaw. We have got to redo this. We've got to make the date, and he won't buy the excuse about the printer.
Well, the printer is not going to be able to get...
What?
What in that?
Electrical failures are always inconvenient. Sometimes they're more than that. This pump is used to put out fires in the plant.
Hey, check the pump, no water.
An electrical failure under these circumstances could spell disaster. There's nothing you can do to a light bulb in the way of preventive maintenance. You just change them. But good preventive maintenance does pay off as far as DC motor controllers are concerned. Now, we're going to go over some of the typical problems you're likely to run into with controllers, what causes them, and what you can do to prevent them. We'll concentrate on the components in the control circuit and the controller itself. Before we start working on this controller, we must make sure it's electrically isolated and tagged out. The chief hazards to electrical equipment are dirt and contamination. Slowly and surely, they eat away at a component's ability to function. Get rid of any clutter that's accumulated on the controller. Now, some people think nothing of setting an open can on a cabinet until it spills. You've got to keep both the exterior and the interior of the controller clean. Now, see these? They're usually the only source of ventilation the controller has. Keep them clear. Check the cable entrance connectors. The connections should be tight. Make sure the doors are in good shape. Check the condition of the hinges. Somebody mistook this for a cupboard. Light bulbs, rags, trash, goggles. Probably a change of socks, too. Nobody should use a controller as a storage cabinet. Take the time to clear out litter when you come across it. Check the condition of the wiring. Look for frayed or cracked insulation. See if there's any evidence of damage from heating. That includes charred or melted insulation. When you've got heat damage, the copper connections turn a dull reddish color. In extreme cases, they blacken or flake. You have to clean them up in order to determine if they're okay. You'd also want to clean up the connections anytime you replace a component. Electrical connections are extremely important. They need to be both electrically and mechanically tight. Tight means different things to different folks. Electrically tight means making good, clean contact. Mechanically tight means physically tight, especially in a magnetic controller, because all connections are subjected to the additional vibration of contactors opening and closing within the unit. When you get to the contactors, operate them by hand. Make sure they don't bind. Watch the contacts. The movable contacts should strike the stationary contacts before the armature is moved all the way into the coil. Check out the contactors individually for missing pins, screws, or broken parts. Examine the movable and stationary contacts on each one. They've got to be in top condition. On copper contacts, you want to make sure they're not badly burned or pitted. They should show good color. If you see the blackened film we mentioned earlier, that's copper oxide. Remove it. Copper oxide's a very poor conductor. Filing or sanding the surface will smooth and clean the contacts at the same time. Use a contact that's in good condition as a reference when you're sanding a contact. You want to keep the contour of the surface the same as it was originally. Be careful of how much you file, though. If you have to file away so much you can't retain the original contour, throw away the damaged contact and replace both the stationary and the movable contact with a new set. And by the way, we're only talking about filing copper contacts. Silver contacts are something else. Silver contacts may also discolor, but silver oxide happens to be a very good conductor, so don't file away the film. Then go on to the armature. The face of both the armature and the iron core should be clean. Remove all traces of rust or other evidence of contamination with fine sandpaper. If the pivots in the movable armature have bearings, make sure they're in good condition and that they're not binding. Don't oil contactor bearings. In fact, keep all lubricants out of controllers unless specifically required by the manufacturer. Lubricants collect dirt and dust, so they can cause the controller to operate sluggishly. Look at the contactor coils. Watch out for signs of heating, such as damaged insulation. Replace any that you think are suspect. Look over each component in the controller carefully. Use the manufacturer's manual to verify that each one, the overload heater for example, is the right size. Check any fuse holders. Make sure the connections are clean and tight. Check for proper oil level in the time delay dash pots. There seems to be a million things to check, but check them all. It's worth it. It does prevent foul-ups, and that's the name of the game. Oh, and as you go along, make notes of things that are going to need attention if you can't fix them on the spot. When you're sure everything is just as it should be, get a hold of the sequencing chart and check the controller for sequence. Watch the contacts for flashes or sparks. This is an indication of contactor bounce. It happens when the contacts come together, then immediately bounce backward, creating a spark or an arc. Don't forget to check the condition of the control switches in the system that aren't located inside the controller. Their condition is just as crucial to good operation as the ones in the box. Preventive maintenance is no easy task. You've got to be just as meticulous in your approach as you are when you're troubleshooting. But an orderly, systematic approach pays off. The equipment works, and the system delivers when it's needed. You're probably wondering what we need corrective maintenance for if everyone follows preventive maintenance procedures. Well, accidents for one thing. If a forklift backs into a controller, it's the controller that gives. Physical damage can cause electrical failure. Nothing you do in preventive maintenance could eliminate an accident like this. So, let's get down to what you can do. We'll go over some of the typical failures that occur in DC motor controllers and how to correct them. The contactor is the heart of a magnetic controller. It also requires the most attention. The electromagnetic coil can open or short. The contacts can break or become misaligned. They can burn. Contacts can actually get welded together. The mechanical mechanism can bind up. Its parts can break or work loose and block other parts. Most of the time, the coils and contacts are the biggest sources of headache in a controller. You know a lot about what can go wrong with contacts. Apart from chips, cracks, and marred surfaces, you know that they can burn to the point where they won't function. And we've already mentioned that dirty or greasy contactors operate sluggishly because of friction. So what we're going to do now is take this contactor apart, clean it up, check it for damage, and reassemble it. And then we'll operate it by hand to make sure it works. We've already had it tagged out, but before we actually take it apart, we've got to make sure we can get it back together again the right way. You need to mark each wire and each connection point plainly and carefully. You might not be the one who has to put the component back together again. Strange markings make for strange connections. Tape does a good job, but whatever you use, keep your markings clear and simple. Whoever follows up on your work will certainly be grateful. We need to remove the armature to expose the contacts and the magnetic coil. So we've got to pull the pivot pin and pull the armature out. Okay, the contactors apart. Check the contacts. Clean them. File them if you need to, but only copper ones, right? These are silver. This particular stationary contact just unscrews. It's made something like a nut for a bolt. It's no trouble at all to screw on the new contact and tighten it up. There's a general rule about replacing contacts you ought to be aware of. Contacts come in sets or pairs, one movable and one stationary. And they're replaced in sets too, so bear it in mind. You don't replace one, you always replace two, both the movable and the stationary contact in a set. To get the movable contact off, he has to remove the cotter pin and the contact spring. Then it'll come right off. There are a couple of washers in front of the contact spring, and there's a larger one behind it. Okay, he's removed the old one. Now he's got to take a final look at the new one to make sure it will fit properly. After he's got the new contact on, he just reverses the process. First, he's got to put the larger washer up against the new contact. Then he's got the contact spring and another large washer to deal with. Now all that's left are the small washers and the cotter pin. Now, what's happening here? It seems as if he couldn't get them on. They're so small and thin that if he doesn't have them lined up just right, they won't slide onto the contact. Well, seems like he took care of the problem. Now he's got to reinsert the pin. All right, installation is complete. The coil's what we want to look at next. Now, some coils are harder to get at than others. You'll come across a number of different kinds. This molded case coil is used a lot in the more modern controllers. The coil he's working with is easy to get at. To get it out, you just bend back a couple of tabs and pull it right off the core. You want to inspect the coil carefully. Well, we're ready to put the contactor back together again. First, we'll put back the coil. Make sure you line it up with the armature so it won't get hung up on the core. You want it to slide on easy. Push the coil onto the iron core. Bend the tabs back with a blunt edge tool like this so you won't damage the coil insulation. The next step is to install the armature. Line the armature up with the stationary part of the contactor and install the pivot pin. Sometimes it's a little hard to do. He seems to be having some difficulty here. He's going to have to fiddle with it until he can get that pin to slide into the holes. Okay, the pivot pin screws installed next. This screw keeps the pin from sliding out when the armature moves. You know that the pivot pin is critical to the operation of a contactor. It connects the movable part of the contactor to the stationary part. Now this screw holds that pin in place, so it's just as important as the pivot pin itself. You remember what happened earlier when a piece of a contactor got loose and fell off. So he's making sure that screw is on as tight as possible. Use your markings to guide you as you connect the wires to the coils and the contacts. Well, all that's left to do is check that it works. Operate it by hand a few times. Make sure it doesn't bind. Look at the contacts to be sure they're properly aligned and making good contact. We followed the markings, so it should be hooked up and it should work. All the procedures we've outlined, troubleshooting techniques, preventive maintenance methods, and repair methods will all work if you apply them carefully. Successful troubleshooting depends on accurate analysis, good observation, and meticulous attention to detail. Maintenance methods always require the last two, if not all three. It's impossible to develop all of these skills at once, but if you practice the techniques, they'll come.